So we're about to start. Do we have Destiawan here? And do we have Penli? Those presenting in the next session, please, if you're here, kindly come forward so we can stick to time. Okay, we still are missing two presenters. Okay. So one last call before we start the session. I'm looking for the presenter for, the paper Evaluation and Resolution of Identified Issues at CTBTO Auxiliary Seismic Stations in Indonesia. I have Destiawan here, or Rizkita. If you are any of those two, please identify yourself. And then second paper, Optical Fiber Sensor-based Transportable Active Seismic Survey System Solution to On-Site Inspection by Penli or Kinley or Yelang, and the rest. Okay. Is that one of the presenters? Okay. The group is here. So who's speaking? Who speaks for the group? Okay, please. All right, but so while she's, she, am I right? He, okay. While he's coming up, we actually do have a first presenter ready and set to go. This is our session on systems engineering for international monitoring system and on-site inspection. And so basically, we're looking at the monitoring systems and the on-site inspection. I'd like to, I know that we have a number of subject matter experts here, but I'd like to encourage the presenters to speak a little slowly, even though we'll keep to time, but speak a little slowly because it's a multicultural group. It's also a multidisciplinary group, so people may not be exact experts in your own area. So speak clearly, slowly, and ensure that you communicate and carry everyone along as much as possible. But keep your eyes on the clock because we'll be quite strict with that one. As it is, some of our keywords, we're looking at power systems, we're looking at system refurbishment and modernization, we're looking at communication infrastructure, sensor network design, and operation. Well, by the way, I'm Doyo Dubanjo. I'm from the Nigerian Academy of Science and also the International Network for Government Science Advice, and I'm moderating the session, as you can see. And I have Irene Bianchi with me, who's keeping the time, and she's very good at that. So please, a round of applause for Jean-Airo Bolanos from Costa Rica, who's speaking on Comprehensive Nuclear Test Ban Treaty instrumentation under extreme tropical conditions, and giving examples from Costa Rica. Please, a round of applause for him.
Well, good afternoon, everyone. My name is John Bolanos. I am from Costa Rica, and I work for the Volcanological and Seismological Observatory of Costa Rica, OPSICORI. Today, I come here to talk a little about some problem that we found in Juntas of Avangares station due to the extreme climate of the tropics. Well, the operation CTBTO instrumentation under stress condition, an example for Costa Rica. Well, at the beginning, I present you the station, the JTS station located.
Sorry, Pardon my interruption. I just thought I should tell you it's 12 minutes.
Yeah.
And then again, 3 minutes to ask you questions. So
Okay.
sorry, carry on.
It's okay. All right. Well, the station is integrated into the CTBTO project network since 1996. It is located in Central America, Guanacaste, Costa Rica, located inside an abandoned gold mine covered by a large tropical forest and sources of measure. A lot of humidity. We have a lot of humidity in this place. It's going to be very important in the presentation. Here you can see Costa Rica is located in middle of the Pacific Ocean and Caribbean Sea. Is why we have a very rainy season, especially in the mountains, where is located the station. You can see a little of the average, the weather conditions. We present an average temperature of 27 degrees. Per year, we have a yearly precipitation of 2,281 millimeters per year. Is a very high quantity of water. The solar radiation per day is around 15 to 24 megajoules per square meter, and we have a long rain season. Is too important because here we have the combination of the heat and the humidity. The factors produce a large quantity of humidity and condensation that little by little infiltrates inside the bunker and insulating boxes. This is a big problem that we have in the station. Well, first I'm going to start explaining a little of the effects of the extreme conditions. The manufacturing indicate that we have affection is the UTP cables are affected for the high temperature. We have the standard with 21 degrees. We can see that we can have a channel of 100 meters and a permanent link of 90 meters. But conforming increase the temperature, the length of the channel is decrease. In our case, if we can check with the average is 27 degrees, the length of the cable decreased 3 meters. This is something important, but is even more important the consider the effect of the humidity in the cables, in the UTP cables, which consists on a return signal that can be interpreted by the system as a periodic signal. In our case, we had a 120 seconds signal in our system. Other is important, take in consideration the instrumentation. We have two seismic digitalizer, Q330HR, two seismic broadband sensors, STS2.5 and STS6.0. And we have a redundant telecommunication system. We have VSAT and cellular modem. This means that we have a redundant infrastructure. Here you can see how is the installation, where inside the mine we have the instrumentation, that we have the sensor and the digitalizer, but we communicate or digitalizer with the bunker, where is the communication, is to 50 meters, and it is going to the bunker. Well, in the network diagram, we can see how the equipment must communicate with the bunker. This means that of a communication cable of around 50 meters, and it is going to the bunker where the data is transmitted through a redundant communication system. Well, why is important the correct data acquisition? We continuous operation of the CTBTO geophysical instrumentation worldwide has proven to be extremely important for characterizing sources, process, and atmospheric effects associated with the nuclear and chemical tests, especially during complex political climates. This observatory have also strengthened the geophysical monitoring capabilities of solid earth processes like large earthquakes and volcanic eruption on Earth, exponentially increasing CTBTO value nowadays. Well, the challenge to keep the station running correctly. Assuring the correct functioning of this instrumentation is hard under the extreme conditions of temperature, humidity, flora coverture, and complexity of the tropical forest. In summary, in the station, there is a combination of high temperatures and humidity, and it is a bad combination of conditions to installing a long cable for the communication. The problem, considering the aspect explored at the beginning, on the presentation, we show how under extreme conditions and current infrastructure, the use of UTP cable for data transmission can generate electronic noise of a long period that dramatically affect the quality of the data. In our case, a long period noise of 120 seconds was generated. The solution was implementation. We replaced the UTP cable with fiber optic to reduce the effect of the high temperature and humidity in the tropical climate, taking advantage of the property of fiber optics and the transmission of data on this material. On this occasion, the decision was made to replace to fiber optic. For this reason, when necessary, change the switches too. We have a regular switch and was changed to a fiber optic switches, and the change of UTP cable for the fiber line is the change that we did, and with that we take the advantage of the fiber optics. What are the advantage is work with light. We don't have electricity in the cable. And in this reason, the noise disappears, increasing the increase the distance. This means that we can send our data to a long distance, a very long. We increase the distance. We decrease the interference of the humidity. And what was the result? The result was no noise in the data. The 120 seconds noise disappeared of the signal, and this a long period. With this, a cleaner and more appropriate signal is available for the analysis inside the observatory. Another improvement that we did in this project was use an external antenna to transmit to take the signal inside the secondary communication system that is a modem. This modem had a problem. They have a very, very low signal intensity because the bunker works like a Gauss, cage and attenuate the signal. With the use of an external antenna, we increase the signal inside the bunker. And for this reason, we now have a redundant and stable transmission systems with the VSAT and the modem system. The VSAT is the main, but when we had problems like produced by storms or hard winds, we can use the network, the regular network, and it works very good in this area. 2 minutes? Okay. And that's it for now. I don't know if someone has a question.
It's first already. Thank you very much, John. So we have, sorry, let me just ask again. Is Destiawan around or is Kita? He's here. Please come to the front now. So I needed to know that so that we'll know if we overshoot time. But since he's here, we can't. Do we have any questions for John? Any questions? So he talked about improvements to cater for extreme weather conditions, the changes, modifications they made. Any questions? It looks like John is getting a free pass. Yes, sir.
Can you explain what part of the cables were replaced with fiber? Was it from the sensor to the digitizer or telecom? Thank you.
The cable that we replaced was the communication from the interior of the mine to the bunker. It is between the digitalizer to the transmission system. Yeah, it's the part that we can replace in this case. Sure.
Okay, great. Thank you. Any other question? Going, gone. Okay, another round of applause for John, if you please. Okay, so we move to the second presentation, which is the evaluation and resolution of identified issues at CTBTO auxiliary seismic stations in Indonesia, based on incidents reported over the last 5 years. And we have Destiawan Kriswibowo.
Destiawan.
Destiawan. Yeah, I tried.
But you can call me Desta.
No, Destiawan.
Okay.
It's just fine.
Okay.
So Destiawan will be speaking. A round of applause for Destiawan, please.
Okay. My name is Destiawan. I'm presenting about evaluation and resolution of identified issues at CTBTO auxiliary seismic station in Indonesia, based on an incident reported over the last 5 years. And my co-author is Ms. Rizkita Paristuta Asef from CTBTO. Okay. Oh, sorry. Oh, sorry. Ah, it matters.
So Destiawan, you have 12 minutes.
Okay.
And then questions after.
Yes. Right. There were 44 incidents were reported at EMS during 2018 to 2022 for 6 stations, Bati, CG, Jai, Kapi, Lem, and PSI. So most of the problem is instability of the power system at 6 auxiliary IMS stations in Indonesia. Indeed have an impact onto the performance of the station. Seismic stations are equipped with sensitive instruments that measure ground vibration and seismic wave. This instrument requires stable and reliable power supply to function properly. As well as this issue affected also with the GCI link performance in NDC ID. To ensure the reliability of the seismic station performance, it's important to have stable and uninterrupted power supply. Proper power system design, including backup power solution, surge protection, grounding, and regular maintenance, helps mitigate the risk associated with the power-related issues and ensure the continuous operation of the seismic station. Okay. According to the reported cases of power system instability and affecting the performance of an Indonesian seismic station as follows. Power outage. If power outage occur frequently in the area where the seismic station is located, the stations may lose power, disrupt data collection and transmission. Power outage can be cause gaps in seismic data, and ensuring accurate analysis data and interpretation of seismic data can be difficult because we have gaps. Data loss. Power system instability can lead to voltage fluctuation, surge, and power spike. The electrical disturbance can damage the electronic components of the seismic station, including data loggers, sensor, and communication system. Data loss or corruption may occur, impacting the reliability and accuracy of the seismic data recorded by the station. Okay. Noise interference, of course. Unstable power system can introduce electrical noise into the operation of the seismic station. This noise can interfere with the sensitive instruments, leading to distorted and contaminated seismic data. Contaminated seismic data. Electrical noise can make it challenging to identify and analyze seismic signal accurately, potentially affecting the station ability to detect and report seismic event. Communication issue, seismic station often rely on real-time data transmission to central monitoring station or data analysis center. Power system instability can disrupt communication channel, causing the delay or interruptions in data transmission. This delay in data reporting may hinder timely response effort on scientific research related to seismic activity in the region. Okay. Following challenges of improving the power system. The commonly problem is, and the major problem, there's no fund or budget allocation for this station's sustainability. Second challenge is remote location. This location often lack of reliable power infrastructure, like 220 volt AC. So making challenging to establish the stable power supply. Extending the power grid to this remote site can be logistically difficult and expensive. And the second one is natural disaster. This event can cause damage to power infrastructure, including transmission line, substation, and generators, affecting the reliability of the power supply. Implementing power system improve that can withstand and recover quickly from the disaster as is crucial. Maintenance and support. Maintaining and servicing the power system at the seismic station can be challenging, particularly in a remote location. It may require trained personnel and specialized equipment to diagnose and to repair the power-related issues, ensuring a consistent supply of the spare part and having an efficient maintenance plan is essential for sustaining the reliability power system. Management of priority and decision for station sustainability. So if we have more than one station, we have to prioritize which data will give the, which more important than the other station. That decision that we have to make. Okay. Combine of those challenges and problems usually are the main cause of the some time to solve the problem. Immediate response and action are on hold because those challenges and obstacles. So we cannot react immediately to solve the problem due to challenges that I mentioned before. Okay, how can this be mitigated? Several measures can be taken to mitigate the impact of the power system instability on the seismic station performance. First, we can do backup power. Seismic stations should have better backup power source and technology. Lead acid battery should be replaced with the lithium battery because it's more durable. New hybrid solar charge control technology also could be used combined with the 220 volt AC if we have in the location. This backup system can provide temporary power during power outage, ensuring the continuous operation of the station and the preventing data loss. So you can see this lead acid battery and lithium. So we should move to the lithium one. And then we can, you see there's two solar charge controller. Those solar charge controller is using two sources. It's from a solar panel and also from 220 volt AC. Okay. Several measures can be taken to mitigate the impact of the power system instability on seismic station performance. Redundant power sources. Implement the redundant power source such as backup generators or renewable energy system to enhance the reliability of the power supply. Backup generators can automatically activate during power outage, ensuring continuous operation of the seismic station. Renewable energy systems such as solar panel and wind turbine can provide sustainability power in areas with the limited grid access. Power system design consideration. When designing and operating power system at seismic station, consider factors that enhance stability. These include proper grounding techniques, electrical insulation, to sensitive instrument, and voltage regulation mechanism. Design power system is flexibility and scalability in mind to allow for future expansion and or integration of the new technologies. Consider re-evaluation and redesign of the power system at 6 auxiliary stations of CTBTO will be one of the aspects and improve the station performance. Okay, this is the illustration, if you can see.
That's when we're actually out of time.
Oh, out of time, okay.
Yeah.
Okay, continue. So, sorry. This is the configuration of the combination with the solar panel with the 220 voltage AC. You can see on the right, it's not using battery integrated with the solar panel controller, And on the left is the battery is integrated with the solar panel controller. Okay, make it quick. Installing power conditioning, installing power condition and equipment such as voltage regulator and surge protector can help stabilize the power supply and to supply the seismic station. Smart UPS at NDC also provides stabilized power supply to server network. These devices can mitigate the effects of voltage fluctuation and protect sensitive equipment from the electrical disturbance. Grounding shielding, proper grounding and shielding technique can help minimize the electrical noise interference by the seismic station. Grounding system should be designed to direct electrical current and reduce impact of the electromagnetic interference on the instrument. Okay, for make it simple, this one is field operator equipment and standard operating procedure. Proper equipment will help field operator to measure as accurate as possible. Accurate weight will identify the problem and implement proper troubleshooting. So if you, on the old days, we only using the standard alphometer, but now if you want to check the battery, we should have some device made from Medtronics to measure the CCA rating. That is give more accurate result than the voltage we measure with the alphometer. And for the communication, we can use the spectrum analyzer to point the antenna with more accurate. Okay, regular maintenance and testing. Implement proactive maintenance and testing to ensure reliability power system. Regular inspection, equipment calibration, and preventive maintenance can help identify potential issue and address before the seismic system preventive maintenance can help identify potential issue before the problem is getting worse. Okay, this is the monitoring that we have. We should add more because the existing monitoring is only monitor voltage from the battery from the remote side. If we have more information from SEC, we can have something to work on before we go to the remote site. Okay, conclusion, by implementing this measure, the impact of power system instability and on the performance of the seismic station can be minimized, ensuring the reliability and the accurate seismic data collection and analysis. Consideration of power system re-evaluation and this redesign at 6 Indonesian auxiliary stations with support and advice from PTS and CTBTO is potential way to improve the station power performance. And we also like to thank you for the PTS for their support, because from their support, our site, we are as a station operator, we can collaborate and improve the maintenance and to improve the data reliability.
Thank you very much. Thank you. Thank you, Destiawan. And my apologies for the interruption again, but I think it helped because you wouldn't have been able to finish on time at all. Yes, so I think it was a good accident. So any quick question for Destiawan? Anyone? Yes, sir. I think you need the mic because of the recordings and the online audience. Thank you.
Thank you. What is not clear for me is what did you solve? What remained to be solved?
The same problem with us in here is we can solve the problem in the remote site, such as a battery and the pointing and the disaster. We have a typhoon last year, and then the pointing is changed and realigned again. But the commonly is the battery issue. So we use new equipment like Medtronics that I stated before, because if we just use the alphameter, it cannot be. So what is remaining now, the problem in the batteries. Because the battery is only 2 years, but we need to change to lithium so it can become a 10 years reliability. Thank you.
Okay, great. Was that's clear enough? I think so. Thank you. Any other question? Very quickly for Destiawan. Okay, going, gone. Great.
Okay.
So last but not least, another round of applause for Destiawan, please. Thank you. Last but definitely not least, we have a presentation on optical fiber sensor-based transportable active seismic survey system solution to on-site inspection. And speaking is Penley. Like I said, speak slowly. Where's the control? Okay, great. So Penley is speaking. Again, I want to be sure he's listening. Speak slowly, clearly,
Okay.
as much as possible, but you have 12 minutes.
Okay.
All right, thank you.
Good afternoon, ladies and gentlemen. I'm Qin Li, come from China. The title of my presentation is Optical Fiber Sensor-Based Transportable Active Seismic Survey System Solution to OSI. The report includes 4 parts. 1. Introduction. Seismic measurement technology is one of the most commonly used methods both in IMS and in on-site inspection. The active seismic survey is one of the technologies that could be used to identify and measure the effects of an underground nuclear explosion in the surrounding geological structures. The active seismic survey has advantages as follows: deeper detection depth, higher accuracy, suitable for more complex geological environments. The second part, method. This is the typical deployment scheme of a typical active seismic survey system. The system consists of sensor demodulator, sensor array, vibration source, recorder, and processing server. Sensor array consists of acquisition train and main cable. First, acquisition main train is composed of area insertion, couplers, and optical sensors hanging on the main cable, and it is based on time division multiplexing technology. 2. Fiber optic seismic sensor. It is based on Michelson interferometer, consists of sensitive cylinder and mass block. We wrap optical fibers on the sensitive cylinder can form a fiber ring. Then we analyze the sensor by thin shell theory and elastic mechanics. The sensitivity and the resonance frequency are influenced by Young's modulus, cylinder thickness, and the weight of the mass block. So after analysis, we can obtain the frequency response of the sensor. With 500 Hz, the frequency response of the sensor is quite flat. 3 are the seismic data acquisition equipment. Include fiber optic main cable, fiber optic demodulator, and seismic recorder, including acquisition software. Fiber optic main cable based on wavelength division multiplexing and space division multiplexing. Fiber optic demodulator based on array modulation and demodulation technology. Seismic recorder is used to collect and store seismic data deflected by formation. 4. Procedure of active seismic signal processing. It includes 2 key technologies: weak signal extraction and inversion modeling and analysis. 5. Matched fettering algorithm based on Hilbert transform. The advantages are as follows. The constructed signal maintains the basic characteristics. Prediction of high frequency signal without false frequency and a small amount of calculation. This is the actual data processing result. We can see surface wave energy is effectively suppressed, and weak seismic signals is effectively extracted. 6. Deep learning method for denoising based on FFCNN. The problems of conventional denoising methods are as follows. The assumption of the algorithm are inaccurate, and the parameters of the denoising process are improper due to manual inversions. So then is the architecture of the method. This is the actual data processing result. We can see it can eliminate the random noise and retain the useful seismic data effectively. And the denoising image quality has been significantly improved. 7. Multi-card and multi-node for waveform inversion technology. There are problems as follows. Full waveform inversion consumes massive computing resources. Use multi-card, multi-node is suitable for inversion. So this is the hardware strategy. Through model division, multi-GPU card, multi-mode parallel communication technology, high precision characterization of deep geological structure is realized. This is 8. 3D tectonics modeling. This is a 3D slice display of the seismic data volume and 3D display of the structural layers surface. This is the third part, results. At geological surface, the vibration source used to excite the seismic wave, and the sensor deployment, the position of error test, and the last picture is debugging inside the instrument vehicle. This is the fiber optic acquisition chain and main cable have withstood the test of the sudden floods, as it means the robust operation and resistant to crashes. This is the result. The fine geological structure is constructed and the tectonic layers is displayed. last part. Conclusion. The system solution to active seismic survey based on optical fiber sensor array meets with the technical requirements of OSI Act. This system is adaptable to any seismic sources. The system has been tested and verified in field and can be suitable for future OSI IFE. That's all. Thank you for the attention.